a little bit because we were running late, so there was no time for questions. I don't know if we should start. I mean, we could start with some questions. If you have some questions concerning the last lecture, there was no time to ask. You could ask now, or of course you can also wait until later. Are there any immediate questions concerning the last lecture? Yes,
not aware. Are the slides available?
Okay, so there's a question about the slides being made available. I guess this is something we discussed separately, but I think if you agree to have your slides made available, then we will make them available on the website afterwards.
They can be made available.
Yeah, so I think the answer is yes, we will make them available. Okay, very good. So then let's get started with the third lecture by Philip. Please, go ahead.
Thanks a lot, and let me apologize for going so much over time last time. I simply got confused about how much time I had, and so I thought I was within the time, but I was not, and I will try to make it up to you today, not by going over time again, but maybe not going before an hour and 15 minutes, and then leaving some time for questions at the very end. So let me go to the point where I was, and see if I can find it. I have tried to summarize what I have been doing. So here is a summary of the models that I have been discussing, and I noticed I made a mistake here. So this is the many-body Hamiltonian. For the n electrons moving in an atom with a nuclear charge Z. And the ground state energy, QZN, was the infimum over all antisymmetric wave functions of space and spin. So I'm not giving all the details here, I'm just trying to remind you. Then we had some simplified models, or the models that were simpler, and there was the Hartree-Fock model where we restricted, we could write it again like this, but it was for psi's that were Slater determinants. And in that case, it was possible to rewrite the energy only in terms of the gamma, which was the one-particle density matrix of the Slater determinant, that gamma was a projection of trace n. But we saw that it was actually, one could relax the minimization and get the same answer by looking at trace class operators between 0 and 1, they needed not be projections, emphasizing that the trace is again n, but now not a projection, and then calculating the energy as a function of such a gap. Sometimes it's called an admissible one-particle density matrix. And the Hartree-Fock functional, well, I will define it down here, remind you of the reduced Hartree-Fock functional, and the difference between the two, between the Hartree-Fock functional and the reduced Hartree-Fock function, is that the Hartree-Fock function, you also subtract the exchange term. And I'm not writing down the explicit form of the exchange term now, but it was on the previous slide. And then the reduced Hartree-Fock model is what you get by not including the exchange term, so that has the kinetic energy, the attraction to the nucleus, and that part here is sort of one body part that just depends linearly on gamma, so that this is a trace of this, actually the hydrogen operator against gamma. But then we have the electron-electron repulsion, which in the reduced Hartree-Fock model is approximated by the self-energy, the electrostatic self-energy of the density rho gamma of x that goes with the density matrix gamma. So that was the reduced Hartree-Fock model, and then we have the Thomas-Forney model, which depends only on the density. So the function, non-negative function with an integral n, and you calculate the energy from evaluating that functional. And the functional was that the kinetic energy minus 1/2 Laplacian trace gamma was now replaced by its semi-classical approximation, which gave this expression, which was the integral of 5 first. The other terms are actually exactly the same as they are in the reduced Hartree form. So these were the 4 basic models that we were looking at, but then I also introduced what I call the Thomas Fermi mean field model. And I've written it here in a form that's a little bit suggestive of what I want to use it for in a little bit. So I've actually written it as a many-body model, but it is really an independent electron model. So I'm again taking a psi, and I'm taking the infimum of psi for a, and actually I'm doing this only in the case when, so this is also a mistake, I'm actually doing it only in the neutral. I mean, it's not a mistake because I wrote up here that in the C, but I want to emphasize that it's the, I'm only doing this for the neutral atom. So we again have now a mean field operator here. This is the Thomas Fermi mean field potential this time. So we have that the particles are moving in this potential, and one has to correct to get an energy that's comparable to the energy in the other models. One has to correct by this constant, because in the mean field, in this mean field model, we are overcounting the kinetic, the electron-electron repulsion, so one has to correct for it to get an energy that's comparable with the other energies. In any case, let me summarize the results that we had, and I've sort of tried to color code it a little bit. The thing that's in red, these are things I did not prove. I mean, I didn't prove anything in real. I mean, there were some details, but I put in red something that I definitely did not prove. And in blue here, something that I have not proved yet, but I hope to prove in the next lecture. Again, certainly not with all the details. So for all the models, quantum, Hartree Fock, reduced Hartree Fock, and Thomas Fermi, then, so I'm using the notation that's sharp here with the placeholder for either the Q, the Hartree Fock, the reduced Hartree Fock, or the Thomas Fermi. And then the energy as a function of particle number n is a decreasing function, and it's actually constant. So it decreases until some constant value, and from there on it's constant. And we know that this value is less than or equal to 2z plus 1 in all the models. We know better in some models, and I'll get to that. But this is, and we actually do know better than this. So this is not the best result that we have for any of these models. Even in the quantum model, we know, for instance, that asymptotically, so it's known in all of these models that asymptotically, so if you calculate this as a function of z and divide by z and take the limit z to infinity, then this is actually, this is also known. But this I have not discussed. But in the Hartree Fock and in the reduced Hartree Fock model, and that's what I would like to prove in the next lecture on Thursday, we know that the critical, this NC, oh, that should also then have been a sharp right there. For those two models, this number for which the energy becomes constant is actually less than or equal to z plus the constant. So that would of course imply this this relation here, that the critical divided by z. And in the Thomas Fermi case, we actually saw that it was equal to z. So it was convex, it was decreasing down to z, and then it was constant. And for the two models, the reduced Hartree Fock and the Thomas Fermi model, we know that this energy as a function of n is a strictly convex function. I mean, it's decreasing, strictly convex for n less than or equal to nc. Then we also discussed how well they approximate. So we saw that the quantum energy, the one that we're really interested in, the quantum energy is less than or equal to the Hartree Fock, because the Hartree Fock was restricting the class of minimizers, and the Hartree Fock was less than reduced Hartree Fock, because we, in reduced Hartree Fock, did not count the exchange, which has a negative. So we knew that the quantum energy were less than, that we had these inequalities, But then we also proved that this reduced Hartree-Fock energy was actually not much lower than the quantum energy. Well, we could estimate that there was a lower bound with a constant that was equal to 7/4. And I note that the 7/4 actually 7 divided by 5 is actually less than, somewhat less than 8. That's a correct quality analysis. Then we also discussed that we could compare quantum energy with the Thomas Fermi energy. And that was a semi-classical approximation. I didn't do it in detail, but I did argue that from the leading order semi-classics, one would get that the quantum energy to leading order is z to the 7/3 times the Thomas Fermi energy of an Thomas Fermi atom with nuclear charge z and 1 electron. But actually, from the scaling of Thomas Fermi theory, this quantity here, z 7/3, is actually the Thomas Fermi energy of an atom with nuclear charge z. So maybe let me just also point this out, that E, Z, Cf of the neutral atom is actually equal to this z 7/3. EGF1. But then we discussed that there were corrections to that. There was the thing called the Scott correction. One had z squared, and then there was a z5 correction, which was named after Dirac and Schwinger, that contributed to 2 different parts of the contributions to that term, and then with the lower order, little o of z5. So this I certainly did not discuss. Moreover, we discussed that this mean field Thomas Fermi problem was actually a good approximation up to little o of z squared. What I did prove, and this was actually the same as the proof when we proved the lower bound on the quantum compared to reduced Hartree-Fock, we also proved that, and I guess here there is I really made a mistake. I'm sorry, this should be the mean field. Mean field Thomas Fermi. I'm sorry. So what I'm saying here is that the mean field Thomas Fermi problem that we have up here, and when I subtract this constant, then this energy you get when you minimize this operator, before you minimize, as an operator in the quantity, this object, this operator here is less than or equal to the quantum many-body operator with an error which is again a constant z to the 7/4. This is one half of this inequality. This is the lower bound of this inequality. The thing I did not discuss was the upper bound of this inequality, which is to actually do a semi-classical approximation, find the semi-classical approximation to the ground state of this, to the negative the projection onto the negative eigenvalues, and show that you can actually do this to an order that is better than little o. In any case, these are what I have discussed so far. But what I would like to get to now is more in the direction of periodicity and universality, which is what was my motivation to start. So there's really 3 results that I would like to discuss, but that's not quite true. I'd like to discuss the first 2, and I will leave the last result to the lecture August is giving on Friday. So the first result is what I started saying something about over here. At the very beginning is an Aufbau formula derived by Fermi. That's not quite true. I mean, Fermi did an approximation. So historically, Fermi did this before Madelung had, strictly speaking, formulated the Madelung rule for filling in the atoms in the periodic table, in which order to do it. The thing that I had when I had the Janet periodic table, But Madelung just more or less formalized it. It was essentially known what the periodic table looked like, and Fermi knew what he was trying to explain. He was trying to explain the structure of the periodic table. He came up with a formula and compared it with the periodic table. And I'll get to that a little bit later. But this formula is actually a theorem now, so, and let me just give it here, and then I'll explain the proof in a moment. So, if we take the true quantum ground state, so I call that psi z, this is for the neutral atom. Now again, this thing may not be unique, so, I'm just choosing one. For each z, I'm choosing I know that there's a ground state for each z, and I'm choosing one. And I would like to count how many electrons are in angular momentum L orbitals. Now, the psi z may not really have anything to do with orbitals at all. I mean, it's not as, first of all, it's not a Slater determinant, so what do I even mean by orbitals? Well, you can talk about what's called the natural orbitals. The natural orbitals mean you would take the one particle density matrix, the gamma psi, that's what I've written here, and you may expand this in its spectral decomposition and say that the eigenfunctions are the natural orbitals. That is what we call the natural orbitals. But again, they will not necessarily be eigenfunctions of angular momentum. Just because the atom as a whole is spherically symmetric does not mean that, first of all, does not mean that the psi has spherical symmetry, and it does not mean that this gamma psi z has natural orbitals that have angular momentum quantum numbers. Nevertheless, we can still ask how many, what is the occupation in the psi z in angular momentum L. So what you do is you take the projection PL on the space L2 of R3 with values in C2. You take the projection onto angular momentum L. And then you count how many particles are in this angular momentum L sector by simply taking the trace of PL against the gamma, the one particle density. So that's the occupation in the angular momentum L sector. Now, this projection is an infinite dimensional projection, but gamma was a trace class operator, so this is some number. I wrote it as NL of z, but as I just explained, it need not be an integer, and it may also depend on the psi, because the psi z. Because the psi z was not unique, and in principle, I don't know that these numbers here would be independent of the psi that I'm choosing. But I'm suppressing the dependence on psi z since it will not really be part of it. And then I say that if you calculate this occupation number, NL of z, here, you divide by z to the 2/3, then we're not able to prove that the limit of this exists as z goes to infinity, but we're able to prove something about the lim inf. And I'll explain why we can only prove lim inf. We can get the lim inf when z goes to infinity and the angular momentum L is of the order z to the 1/3. So here I made it rather precise, where we can prove it's actually the ceiling of, so it's the integer bigger than or equal to lambda z. L is an integer, so you have to find a way of making lambda z to the 1/3 into an integer. So what we were doing here was say that L be equal to lambda z 1/3 and the integer which is just bigger. And then the limit, let's look at the limit as z goes to infinity. Then we can find that the limit of this is given by something. So this is true when we have the sequence psi z of true neutral ground states of the atom. Now I'm calling this quantity here phi lambda, kappa lambda, just to have a notation for it. The 4 lambda kappa. The 4 lambda really comes from the degeneracy, that's why I sort of took it out. But remember that there is a degeneracy in each angular, if you fix an angular momentum L, then you will have a degeneracy from spin and from the z direction of the angular momentum, so you would have a degeneracy 2 times 2L plus 1. I'll explain exactly what this degeneracy means in a second. So this is some integral, so this is some function lambda kappa of lambda, and Fermi had this formula in his paper from 1927, but I'll come to this in historical things in a moment. So what I want to do in this lecture is actually to prove this one. Now, what I want to do in the next lecture on Thursday, the last one, I want to talk about more of the universality result, and this I cannot do in the quantum model. So this result here, I emphasize, that's in the quantum model, but again, it's something where you have to choose the angular momentum large, and you have to look at sort of bulk of electrons. If I really want to understand chemistry, and this is what I was also saying earlier on, you probably want to talk about something that happens for a finite number of electrons, and probably sort of the finite number of electrons that are least bound, the ones that when you want to pull out one electron will give you the ionization. I will not be discussing ionization energy because I don't have as strong results for ionization energies, but I'd like to discuss the radius. So recall that I defined the radius as in the Hartree-Fock model or in the reduced Hartree-Fock model. I defined the radius to the last m electrons. So that means you take the radius so that when you integrate the density outside this radius, you have m electrons. M need not be an integer, right? Because we're just, so when I say we have m electrons, I mean the density integrates to the number m. And look here, there is a combined limit here in order to prove something. I first actually take the z going to infinity. I wanted to understand universality. I'd like to understand whether the atoms start looking more or less the same when, or at least whether there's a periodicity when z goes to infinity. And I expect periodicity. I expect that there is no limit when z goes to infinity. But, and that's exactly why here I use this notation with the line above and line below. So the line lim with the line below refers to lim inf, and lim with the line above refers to lim sub. And I'm slightly abusing notation because these are really two different numbers, the lim inf and the lim sub. They will not converge to the same thing in general because I do not assume, I do not expect that there will be convergence. I expect that there's periodicity, meaning that there will be some subsequences for which this will converge to one thing, and there will be other subsequences for which this will converge to something else. But there will still be a lim inf and a lim sub. And what I'm claiming in this identity is that when I think of this as a function of m, and now start increasing m, so after having taken z to infinity, I now look at large m. Then I claim that you recover as the asymptotic. So it's clear that when you increase m, then the radius will become smaller and smaller. You're looking at having more and more electrons outside the radius, so as m increases, this will become smaller and smaller. And I'm claiming that the asymptotic in which this actually goes to zero, as m goes to infinity, is exactly the same as it is in Thomas Fermi. Because this thing here is the, I wrote it as RTF infinity m to the minus 1/3, and that would be the same, that would be exactly this limit if you would do it for the Thomas Fermi. Recall that we discussed that the density in Thomas Fermi theory actually would converge to x to the minus a density which was x to the minus 6 times some constant, and this is simply what you're getting when you integrate that function. Okay, so the claim is that there is a constant here, and that you're getting something that goes up as m to the minus 1/3, sorry, that goes to 0 as m to the minus 1/3, with an error that goes to 0 faster as n goes to 1. So that you actually get the radius very accurately described by Thomas Fermi. And let me just go back to to one of my very first slides, where I had a graph, and I will, this was this graph here. In fact, it's this thing right there, where I tried to calculate the radii of atoms in this first group, the alkali. Since I tried to calculate those, and I did it by actually what I'm plotting here, the red curve. The red curve there is actually the Thomas Fermi curve for n equal to 1. I mean, so the radius out to the last electron. Hoping that that is actually good for these alkali atoms, which are atoms that you get just after you've been to a noble gas. So, right, I mean, here we had the noble gases. Actually, I'm wrong. Here we have the noble gases, and we actually don't even see them because we cannot do radii for the noble gases. They don't bind, so they don't really have an empirical radius. But that's not the issue. The issue is that you put in one more electron, and then you end over here, and these are the alkali. So there's this core, and then one electron. So it's a nice, assumption to think that this radius is a good empirical radius to say that that's what you have. You're measuring it out to where the last electron is. And that's what I did here. And I just plotted it against the experimental values, the experimental empirical values that Slater and Bragg had made tables of. And you see this very nice agreement between this red Thomas Fermi curve. This curve here is a function of z, and then the real values. And so I don't have a proof that this is correct, but what I know is that in Hartree-Fock theory and in reduced Hartree-Fock theory, if you look at the curve when m is large, then it is a good approximation to the rate. And that's actually the claim in these. What is the claim in this theorem? Good. So the last result that I will not discuss, but that others will discuss on Friday, is that if you look at the Thomas Fermi mean field model, so you look at this thing here, then in fact there is a periodicity. So what August will prove is that these operators here, this mean field operator, when you look at z going to infinity, will actually converge in some operator sense to some limiting operator, the one where you put infinity here, but understood in the right way, because when you put infinity, the operator is not entirely well defined, and you have to do it through specific sequences. So August will discuss that on Friday. Now let me say a few words about this Aufbau formula of the Fermi's formula for the occupation number and different angular momenta. I just written it again here. Remember that we also calculated it when you used the Aufbau principle. That was the thing that had the way this. I can again just go back and remind you that this was this here, where we had the way we were filling up was we did 2 rows with one angular momentum, then we started the next angular momentum and so on. And we actually did we didn't really, I just claimed the formula, but you can try to work it out yourself, that we actually found that asymptotically this did go like z2/3 with some function And we also compared it to hydrogen, where we know the degeneracies, and we also got Z2 times some function. So I wanted to discuss this comparison. So I wrote them here. This is the Aufbau, I mean the one where you fill in according to these two rows, for example, momentum and so on. And you divide you divide by z to the 2/3, and you look at large z. And again, L here, I always say that L is of the order lambda z to the 1/3. That's sort of the typical angular momentum when you have such a big edge. And we find these two formulas. And the point is that these formulas are all different. So this is not the same as that. It could be that by some miracle this integral happened to be exactly this, but it's not. Fermi calculated this integral and found that it was certainly not equal to. He calculated it, for instance, when lambda is 0. I mean, there's the 4 lambda, but we take the limit of, just this integral when lambda is 0 is one thing that Fermi calculated, and it's not equal to 6 to. So it's in fact small, 6 to. And the fact that it is smaller will actually be a little bit important later. But one thing to notice is that all of these three asymptotic forms have the property that they integrate to 1. Now, I wrote as they should. But what does it mean as they should? It's simply the sum rule that when you sum this over all L, then it will become Z. So if you divide here by Z to the -1/3, so one way to write, I can think of it like this, that if I sum an L equals 0 to infinity, Z to the -1/3, in L of Z divided by Z to the 2/3, I can think of this as a Riemann integral, or the Riemann sum for the d lambda integrals. So this thing here will sort of converge to the d lambda integral of this object. So since the sum is equal to the sum of the NL of Z is equal to Z, we do get the sum rule that the integral is. Okay, but you can check that they're all three satisfied. It's fairly easy to do it in these two cases, then it's simply integrals that you have to calculate. It's slightly more difficult to do it there, but there it actually comes to the fact that when you do this integral, when you interchange the limit of the integrals here, then you end up with actually integrating phi1 to the power 3/2. And the integral of phi1 to the power 3/2, phi1 to the power 3/2 from the Thomas-Fermi equation is the density. And the constants work out just right so that you're integrating the density. Here, the density in the case when Z is equal to 1, and we know that the integral of the Thomas-Fermi density for Z equal to 1 is 1. So that's how you're getting it. So this follows actually from the TF equation. You get the decimal. But they are all three equal to 1. Okay, so let me go through now the proof of this Fermi Aufbau formula again. So this is this formula again. I would like to prove that. And let me say this is a joint work with August, who's talking on Friday, Son Fournet and Peter Manchon. And we haven't published it yet. And I will begin with the bound that I have actually proved. I almost proved. I proved part of it. This was this thing that the Thomas-Fermi mean field was a good approximation to the full quantum energy. Meaning that if I use the gamma psi z, I mean the ground state of psi z, and use it as a trial function. So I use the psi as a trial function in the Thomas Fermi mean field operator. Right? So this is what you would get then by calculating this. Then this is not much bigger than what you get by doing the sum of all the negative eigenvalues of that one. With an error that is little o of c squared. Let me remind you where this came from. This was exactly this result. This result here, that the quantum energy is actually close to that I have this lower bound of the many-body Hamiltonian by the Thomas Fermi mean field problem, and we then get that this is actually, this lower bound here is a good lower bound for the ground state energy because the error is little o of c squared, and you notice that this additional constant, I can forget about it because it means that the psi has to get this thing close to its ground state has to get this close to the ground state in order to get the energy to be little o of c squared. So that is this boundary to an order little o of c squared. And you will see that it's important that I have little o of c squared. I mean, the two terms are both of order z to the 7/3. They are the order of the full energy. Right? So I need to do better than it's not enough to get it just to leading order. I have to get it better than little o of c squared. Okay, but now this operator is very symmetric, so the whole operator is very symmetric, and that means that I can rewrite this in angular momentum, the angular momentum decomposition, so I can sum over the projections PL. The PL commutes with that operator because it's the projection down to angular momentum, and I can therefore write this as a sum over each angular momentum sectors. Notice I'm not using the fact that the gamma psi commutes with PL because I'm not using that because I don't know that. Right? So I'm putting a PL on both sides of the gamma psi, but the PL commutes with this operator, so I can pull that through and put it over here, and it's just a sum of all. And likewise, when I calculate the trace of the negative eigenvalues, all the negative eigenvalues, of course, that splits in the sum over angular momentum sectors. This operator here, minus 1 Laplacian minus 1 CTF, commutes with the PL. So this is the sum of the negative eigenvalues in the PL subspace, and then I'm just summing the whole. But then notice now that I know that this thing is less than that with an error. Of course, it's also bigger than that because this is the smallest you can get here. So I do know that if I pull this on the other side, then I will get something negative, right? And it's not bigger than z squared. So if I pull this on the other side, I will get something positive, right? This thing is bigger than that. So if I pull this on the other side, I will get something positive, but no bigger than little o. But that means that when I compare these quantities there, that each of them, this thing here, each of these terms is bigger than or equal to that. So if I look at the difference between these two, I just said that this minus that is greater than or equal to 0, because this is the minimum I can get, and this is a trial one-particle density matrix, so this is bigger than that. But this is true term-wise. Right? Each term here is bigger than or equal to that, because this is some operator between 0 and 1. Like the PL gamma psi. PL is an operator between 0 and 1. So each of the terms here must be is bigger than each term here. And the total sum is less than z squared, therefore each term in the sum must be less than z squared. And that's what I wrote. That's sort of a terrible estimate, right? I mean, I have an estimate of the sum, but then I estimate each term by the estimate I have on the full sum. Right? I'm using the fact, I know that this quantity here is bigger than that, but I also know it cannot be bigger than an error I need to understand this operator here, the minus 1/2 Laplacian minus phi CTF projected down to angular momentum. That's the thing that I'm over here calculating the negative. I'm calculating the negative eigenvalues of that, and I want to infer something about this trial state from the fact that it's close to the minimum. But now, recall that, so this thing is an operator that acts on this subspace of the L2 space. That's an infinite dimensional subspace. Now that subspace, or this operator, by doing the usual angular momentum decomposition, is actually unitarily equivalent to a one-dimensional operator, namely the operator that I wrote right there. Right? It has the minus 1/2 d squared dr squared, and then because I'm in angular momentum L, I have the angular momentum L times L plus 1, and the 1/2 gives me a 2 over r squared. So this is equal to, this is a function that depends only on r, it's a spherical symmetric potential. So this operator on that space is unitarily equivalent to that operator on a one-dimensional space. I have to worry a little bit about the degeneracy. So I wrote it here that it's an operator on R plus, so the positive real line. And the degeneracy is that you both have the spin degeneracy, but then you also have the degeneracy to L plus from the LZ, the LZ degeneracy in the angular momentum set. But now I want to recall that the phi z TF of R, remember this was z to the 4/3 by 1 TF of z to the 1/3 R. And this is what I used to do a semi-classical approximation earlier on. I'm going to do exactly the same thing. I'm rescaling so that I get an R in. Meaning that I rescale from the Thomas Fermi angular moment, I mean the Thomas Fermi with nuclear charge C to Thomas Fermi with nuclear charge. And when I do that, well, I replace R by Z to the minus 1/3 R, and that will multiply Z to the 2/3 in front of the kinetic energy. But then I pulled out, just as I did before, an overall Z 4/3, right? So that these two together would give me Z 2/3. That's because I multiplied R by Z to the minus 1/3. Then I multiplied DDR by Z to the 1/3, and I end up with Z 2/3. And I pull out the Z 4/3 that I have both in front of the Thomas Fermi potential and here, and I end up with this operator right there. I think it is. Yeah, maybe I just erase it. So we are getting that it's unitarily equivalent. With this up, notice that I had taken the R was again multiplied by Z to the minus 1/3, and then I pulled out the Z 4/3. So here will also be a Z to the 2/3. Not surprising, because this is really like the kinetic energy, so it must have the same Z to the minus 2/3 as the D squared dr squared, which will be part of the kinetic. Okay, so now there is I want to use the fact that I'm choosing an L, which is essentially lambda times Z to the 1/3. That means that L times L plus 1 Z to the minus 2/3 is almost lambda squared. Now, of course, one has to be a little careful here. This is not exact, and one has to estimate it, but for now, I'm just going to say that's fairly easy to do. And we are left with analyzing, when we want to understand this operator in the three-dimensional space, we are left with analyzing this one-dimensional. Right, where I replace the L times L plus 1 divided by Z 2/3 by lambda squared. So I get lambda squared over 2r squared. And you see now how this looks like a one-dimensional semi-classical operator with a small parameter in front of the d squared, the r squared, so I can think of the semi-classical parameter h. I mean, this h not to be confused with that h, doesn't mean I just gave this operator a name, but you should think of this thing here as h squared. Okay. And we're now in one dimension. And then again, we do have a Weyl law in one dimension that tells us what the sum of the negative eigenvalues is for this operator. And I just wrote the answer. If you do the phase-space integral, the sum of the negative eigenvalues of the Schrödinger operator in one dimension goes like the integral of the potential to the power 3/2. The potential is here phi 1 lambda squared over 2r squared. Well, I rewrote it slightly by multiplying the potential by 2. Just one could also put the 2 here and put the 2 outside, but I chose to write. And I left sort of the degeneracy 2 times 2l plus 1. It's true that L also depends on Z, so really on H. But for now, I'm really just counting it as the degeneracy, the 2l plus 1 and the 2. And in one dimension, what you're getting is that the Weyl law goes like 1 over h. And so there is an error which is little over h2. Okay, but we need to understand what is the order of all of these quantities. So recall that the h to the minus 1, that's really z to the 1/3. And the L here, this thing here, will also be of order z to the 1/3. That's all together when I multiply them as z 2/3. And then there was the z 4/3 that I had pulled outside. So there's a z 4/3, a z 1/3 here, z 1/3 there. So all in all, there would be a z 4/3 and z 2/3, that's z squared. So I'm claiming that this is telling me that this operator, the trace of the negative part of that operator, is of order z squared with a constant in front, which is exactly what I calculated there. Now this is then replaced by 4 lambda. I should be careful when I say this is really 4 lambda z to the 1/3. So altogether I'm getting z squared with a 4 lambda and an error which is little over z squared. And that's why it was important that I understand that if we go back here, that this gamma psi actually approximates that energy better than z squared. So I know that this thing here must agree with that to the order system. Okay. And I'm saying I don't really care about this value. I'm not going to use this value for anything. The only thing I care about is that it's of order z squared. And that I know that the gamma psi, the PL gamma psi PL, gets into the same address. And that means that it must have the right number of negative eigenvalues. If it had too few negative eigenvalues, it could not get the right order. So let me try to explain this. But let me first say that what I really care about is what is the number of negative eigenvalues. So the number of negative eigenvalues of this operator, the number of those that I'm summing here, that is the same as the trace of, well, I mean, almost, right? Because I made this approximation of the lambda, so it's the sum over the negative eigenvalues. And this you can also do by Weyl law for the number, and this is again the degeneracy, which I have to count, and then it becomes that formula. Here we recognize this Fermi formula. And the error is again h minus 1 plus little over h. And now when you insert exactly as I did here, that this 2 times 2L is 4 lambda, and the h minus 1 was z to the 1/3. This again had a z 1/3, so now I'm getting the z 2/3 for the number, with an error that is little of z 2/3. So you might think now, oh well, okay, that means that we must have concluded that the number of eigenvalues here must be all the negative eigenvalues right there. But that's unfortunately not true. The only thing we can conclude is, so it does not allow us to say that this thing is close to that number. The only thing it tells us is that this thing cannot be much smaller. I mean, there could be way too many eigenvalues. This could be way too big, because that would not change the energy very much, because these extra electrons or eigenfunctions could just live very far away and not contribute to the energy. But if there are too few, then there's no way that I will get close. So what I am able to conclude is that this number, NLZ divided by Z minus 2/3, the same as the occupation, that's just my definition, is bigger than or equal to what you're getting from the Fermi formula, plus something that is little over 1 as equals to 2. So we do get a lower bound for every single lambda. But I wanted to get a limit, or rather a limit. And that we get by using the sum rule, because we know that the sum over the NL of Z is Z. And then by Fatou's lemma, I can again use, so this thing is 1, this limit, because that's the sum rule. But then Fatou's lemma tells me that I can think of this as an integral of the step function, and then I can pull the integral, the lim inside. The 1z, the z minus 1/3 is what I have in the measure, and the rest will be the lim of the number that I have. So I know that this thing here is bigger than or equal to this integral, and I know that this thing was bigger than or equal to the limit, and the limit also integrates to 1. Therefore, they cannot be different. Then for almost all lambdas, they must be the same. So if you go back and think of the claim that I made in the formula, I said that we get this for almost all lambda, we get this as a limit. Unfortunately, it doesn't mean that I'm getting it, say, for lambda equal to 0. So if I look at finite L's here, I mean, lambda, just L being independent of Z, that's the case lambda being lambda L divided by Z 1/3 going to 0, I don't know that I have the limit in that case. The only thing I know in that case is this lower bound that I put here. I always have, for all L, I have this lower bound. But unfortunately, this lower bound does not tell me that the Aufbau principle is wrong for small L. Because as I tried to say, this Aufbau formula is actually giving you a lower bound to the Fermi. So we cannot rule out that this is actually, giving an upper bound. So we cannot rule out that this is, that the Aufbau principle is wrong in that case. Now, so I just wanted to finish today, I promised to finish earlier today, by this historical remark that Fermi derived this formula in a paper published as part 2 of a 4-paper series in 1927. And paper 1 is actually his paper on the Thomas Fermi model. He actually wrote 4 papers, they're in Italian. In the first paper, he derives, as a semi-classical theory, statistical theory as he calls it, for the atom, he derives Thomas Fermi theory. And then in paper 2, he actually tried to use, I mean, Fermi was a physicist. He didn't just derive a model just for fun, he wanted to use it to explain the periodic table. And he tries to do that in paper 2, and he derives this form. And then compares it to the experimental, I mean, what you know in the periodic table, and did not find very good agreement, because it does not really seem to reproduce the Aufbau. We have also seen that in the limiting, in the asymptotic case, it does not reproduce the Aufbau formula. What is quite remarkable about the paper by Fermi is that he actually calculates this function. So, let me just go back here. He actually calculates this integral. That is actually rather surprising that he is able to do this, because the phi 1 itself is a solution to a nonlinear differential equation. Granted, it's a nonlinear ordinary differential equation, right? It was the one that Laplacian of phi was some constant phi to the 3 halves away from 0. But everything is very symmetric, so it's an ordinary differential. So first he has to solve that equation, and after he's done that, he has to plug it in to this integral and then do a numerical integration. So he has to do a numerical solution to this differential equation and then afterwards a numerical integration. Now, this is probably not very difficult to do on modern computers, but in 1927, I think he probably must have had an army of slaves that calculated it. I don't know. Now, interestingly, there is actually another potential found by chemist physicist Tietz that prove that he has a potential which actually gives you the Aufbau formula in the semi-classical. So it's again a potential that has a semi-classical scaling, and surprisingly, it gives you the asymptote. It gives the Aufbau formula, the thing that I compared to here. It gives you that formula in the limit. Now you might say, oh well, you can always come up with something like that. Well, that's not quite true because it has to do it for every lambda, for every angular momentum. He has this, in that potential. There's only one parameter that is free. He's tuning one parameter, but by tuning one parameter, he's actually able to reproduce this. What you will find is that if you look at Wikipedia or general chemistry textbooks, what is the explanation for the Madelung rule or the Aufbau principle, then it actually refers to this potential as giving the explanation. But that's, in a sense, well, it doesn't make much sense because that formula is only true. The arguments given are all in this asymptotic semi-classical regime, the large, when you replace things by phase-space integrals. And we know that in that case the formula is wrong. So there has to be some other way of explaining the Aufbau principle. Now, one thing one can try to do is to actually find the true eigenvalue, not do a semi-classical approximation, but actually really calculate the eigenvalues of this operator here and see if it reproduces even for the atoms in the periodic table. Does it actually reproduce the Madelung rule? It's possible that the Thomas Fermi potential does that. I don't know of anyone who did that calculation. I've not found it. I think that there might be someone who did it and did not publish it. I just asked a student recently to do this was a bachelor student, so I asked the bachelor student to do it for the Tietz potential. And because it's easier, you don't have to do first solve an ODE and then plug that into the equation, because here this potential is explicit. And actually, it looks like this potential, even for small z, reproduces the Madelung rule for most of the atoms in the periodic table, not for all of them. And the reason is that for certain values of z, there are not enough negative eigenvalues here to actually get room for all electrons. You need to have a neutral atom, so you need to fill in z electrons. But actually there are, for almost half, less than half of the atoms, this does not have enough negative eigenvalues, does not have z negative. As soon as it has enough negative eigenvalues, then you can look at how they are filled. I mean, what is the ordering, and that does seem to agree. We didn't calculate, or the student did not calculate it for all atoms, but in the cases where she calculated it, it does agree with the electronic structure that you find in in the periodic table. Still, there is no real reason for why one would choose this potential. The only argument for choosing this potential is that in the asymptotic limit reproduces alpha. One should really try to do it for the Thomas family potential. And this is something that, I hope to do soon. It's a fairly simple calculation, but I have not done that. So that is what I wanted to tell you today. So thanks a lot for your attention, and we have plenty of time for questions or for a longer break. Thanks a lot.
Thank you very much, and Philip, for another great lecture. As announced, we have time for questions, either about this lecture or previous one, or anything else, really. I think this might be an instance where you're just being so clear that you really don't leave any questions. So let me just ask, so this teats, what is, so you said this is actually just an explicit function, which is written down? Or?
Yeah, it's an explicit function. I don't remember the exact form, but it's something like z divided by r to the 1 plus a constant r squared. It has that form. Right? So as r goes to 0, it goes like z over r. And as r goes to infinity, I mean, there's also some z dependence in here, so that you actually have a semi-classical scale. I mean, it does have the form. So let me rewrite it. So what I do know is that it has the form z to the 4/3 phi t 1 z to the 1/3 r. It still has that form, and this is equal to 1 over r, 1 plus a constant r squared. Yeah, I think it's like that. So it does go like 1 over r near 0, but it goes like 1 over r cubed near infinity. And Thomas Fermi actually goes like 1 over r to the 4 near infinity. But I don't know. I mean, I don't know any argument why this should be. It's usually presented as an approximation to the Thomas Fermi, but I don't know in what sense. Because of course Thomas Fermi is some other function, and I have no idea what it means to say that this is an approximation to that. These are just two functions. They have the same asymptotic at 0.
So, just, I mean, I think you said it, but maybe just to confirm that I understand it correctly, because when I think back as a student, long time ago, when I learned, so to say, about atoms and many-body quantum mechanics, I thought the explanation of the periodic table was basically that if you do what you call the Thomas Fermi mean field model, you write down an effective potential based on the Thomas Fermi model, that will actually explain how the periodic table, right? And now I think you're saying actually nobody has done that computation to confirm that is true.
I haven't seen that computation anywhere. I don't know, if you know a reference, that would be great. I have heard that Walter Hunziker did those calculations, but I think he never published it, and I don't exactly know what the conclusion. So I think what you're saying is true in the sense that is what Fermi did, but Fermi did it only. He did it only for the asymptotic, the semi-classical. So I don't know of anyone who actually did it for finite C, but I may be wrong. I have just done it finite.
But only there you have sort of something to compare with the actual atoms, right?
That's correct. Yeah. That is correct. Yes. But of course, what Fermi did was, I mean, Fermi never thought of large Z going to infinity. I mean, Fermi thought of this semi-classical asymptotic formula as an approximation that would be good for small z. Right? So when he did the calculation, he did it and thinking of and did the comparison for small z, and there it does not quite give the right answer. And even if it does, it would not be. It wouldn't really be convincing. You would really have to find the correct argument, because for small z, this is not such a great approximation. But that is what Fermi did. And it is in his paper.
But did he somehow, I mean, what was his conclusion? He was sort of disappointed that he got the wrong answer, but I guess he must have known he made an approximation.
He did not get quite the right answer. And I think you read some disappointment in this paper. There are some numbers that are not quite the right. And that's what people try to say, oh, what can we do it in other ways? And then they teachers came up with this potential. That if you do what Fermi did, so it gives the right answer. But it's not too bad what Fermi did. I mean, qualitatively it's correct. But it's all just done in this semi-classic base-space integral approach.
All right. So if there are no further questions, then indeed we will have a slightly longer coffee break than planned. So let's thank Jan-Philipp once again for a great lecture. We'll see you again on Thursday. Thanks a lot.